Hey everybody, what we're doing is we are going over Lewis dot structures so we can start doing three-dimensional structures. And so what I'm going to do is I'm sharing my screen, and so you can get to see what I did here. All right, and so here is our answer. It's right here at the bottom. This is the structure. And you can see how I had to do trial and error throughout most of it. All right. And so this trial and error helped me figure it out. All right. And so I'm going to get somebody to do this one real quick. All right. Let me turn my video off here. All right. I'm going to have Ashton. Thank you for volunteering. If you'll come on down and you won't get your video, the video's off. All you're doing is just drawing on here. And guess who's going to walk you all through it? Right. All right, you get to sit at the teacher chair. All right. So if you would write at the top of the paper HCN. All right, that's our compound. All right. Let's do a capital N and stuff, like a regular capital N. That's, yeah, like an N like this. There you go. I know what you mean. Boom, boom. All right. So with that said, what we're going to do is, what's the first thing we do?
We have to find the valence electron.
Yeah, valence electrons, the before structure. So do the before for H, C, and N. Do it right there. All right. What's the next thing we do?
We count the valence electron.
Yes. How many we got?
We have 10.
10. So right up to the side. Yep. All right. And so now we're going to go right here. We'll do just H dash C dash N. We're going to try it with single bonds. Okay. All right, hold up. Before you can do all that, you're taking too many steps to it. So cross that one out just real quick here. Cross that whole thing out. All right. H dash C N again. All right. Now onto the side, write 10. How many electrons are here in these two bonds?
Combined, there's 4.
So 10 minus 4. Would you write 10 minus 4 over here on the side? Equals 6. There you go. Now you have 6 valence electrons to distribute amongst these here. So let's give carbon its full octet. So give carbon 4 valence electrons. Okay. Is that 4? There's one right there. I see it. All right, and that means we use 4 of those 6. That means we have 2 left. So give nitrogen how many? 2. So hydrogen's got 2. Carbon's got how many? 4 plus the shared ones, which is 8. So carbon's good. Nitrogen has got how many?
That's 4.
4. That's not enough. And if you're in period 2, you've got to have the octet. Okay. If you're in period 2, you've got to have the octet unless you're boron. All right. So redo this is put an X on this one here first. There you go. X, nice. Do H dash C double dash or equal sign or double bond N. We're going to try that. All right, now I got 10 valence electrons. How many valence electrons do I have in bonds?
6.
So 10 minus 6 over there on the side. All right, and so I had 4 more valence electrons. Let's give carbon its octet. Yeah, carbon doesn't need that many. It only needs how many? Oh, man, that's ugly. Yeah, H dash C, we did it. All right. Double bond, there you go. All right, and then we had two more still left, I think, because we didn't get four. We did two here, so do two more over on nitrogen. All right, carbon's got how many? If you count the bonded and the non-bonded.
Eight.
8, so carbon's good. All right, nitrogen's got how many? You count the bonded and the non-bonded.
6.
6, so nitrogen's still not good, so cross that one out. All right, and now we're gonna do H dash C triple dash N. All right, and you're gonna do 10 minus how many electrons are in bonds? 8 equals 2. All right, so carbon has how many right now? Count all the ones in bond.
Has 8.
It has 8 already, so I don't have to give any. Nitrogen has how many?
6.
So give the nitrogen the 2. I can't see those in the 2s. All right, good deal. All right, that's how it's done. So good job. All right. All right, so you get the picture how to do that. Let's do one more, all right, of these, and we're going to do a compound called ethylene. Ethylene, it helps make up. All right, we're going to do ethylene. All right, so it helps make up plastics. C2H2. That's or not C2H2, C2H4. Excuse me, C2H4. That's acetylene when I did C2H2. C2H4. All right, C2H4. All right, you're gonna do it on that same slide, or you can do it on a sheet of paper. I don't care. I just need to see it. I'm gonna give you a couple of minutes to do this right now. I'm gonna pause the video. If you're done watching this on video, do this also on video right now. Pause the video and do this. All right, so everybody I checked had it correct. Here is the problem right here. So C2H4, we have 2 carbon atoms, each with 4 valence electrons. That's 8. And we have 4 hydrogen, each with 1. So that's a total of 12 valence electrons. I tried the first method, which was a single bond with everything. And that gave me, that's 10 electrons in bonds, 2, 4, 6, 8, 10. And that gives me 2 extra valence electrons. I gave them to one of them, but the other carbon did not have 8. And so that was not the model right here. I even tried a weird model, and I tried this model where I gave one carbon 3 hydrogens and then bonded it to the carbon. And that didn't work either because this one would have 8, but the 12 minus 10, then the extra 2, this would only have still 6, 2, 4, 6. Then when I did the double bond, it again, I had 1, 2, 3, 4, 5, 6. That's all my electrons. But this carbon has 8. This carbon's got 8, and the hydrogens each have 2. So this is the correct structure here. Okay. All right. What we're going to do now is we're going to now increase the rigor a little bit for our next part. But let me mention something to you with our notes. So, go up. Nope, that's not what I want. There it is. Nope, that's not it either. I'm rocking it. Nope, that's not it either. Jeez, Manetti. Let me just make a new one here. Get out of the way. All right, here it is. Sorry for the delay. What we're doing is we're down over here and we are looking at this slide right before it on 60, 4. All right. And so when we look at the slide before on 64, you're going to see it says a single covalent bond. A single covalent bond is the weakest bond, but the longest. The stuff that's in bold and highlighted and underlined, it's more bold and underlined. That you don't have that. So you need to write that in. So a single bond is the weakest bond, but it's the longest. Okay. The double bond is a stronger bond than the single bond, but shorter. And the triple bond is stronger than the double bond, but even shorter. And so again, how do we judge these type of bond strengths? Is you take a certain amount of a substance and you see how much energy does it take to break that substance. All right. And so you're trying to see how much energy does it take to break that substance. So a single bond takes the least amount of energy. Things that have double bonds take a little bit more energy. And with triple bonds, it takes even more energy. And we're going to give an example of this in just a second. All right. And so example of this is right here. We're looking at this. All right. These are some compounds. This is called ethane. Okay. This is ethylene. This is the one we just did. It helps make plastics. Then this is acetylene. All right, if you recognize they're all carbon-carbon bonds. But the one that's the shortest is the last one. It's got the shortest, it's 120.3 picometers. If you remember, a picometer is 10 to the negative 12 meters. Okay, so they're extremely small, but still it's the smallest. Now, when you're talking about the energy, let me see if the energy is on there. Oh, no, we don't have it there, but we can do this here. When we're talking about the energy, the bond energy, for a single bond, it takes 347 kilojoules per mole to break those single bonds. For the double bond, it takes 611. And for the triple bond, it takes 839 kilojoules per mole. So it takes more and more energy to break the bonds. And you got to think about it. This is the reason why, is that those shared electrons, if you have one pair holding them together, those electrons are attracted to both nuclei. If you have two, that means you have two of them that are attracted to both nuclei, and that pulls them even a little bit closer. If you have three pairs, it pulls them even closer. It's like an extra pull on it. It's pulling in a little bit tighter. Okay, it's like an extra rubber band pulling in a little bit tighter. All right. And so that's what's happening right here. And it pulls them in a little bit tighter and makes it a bond a little bit stronger. There's names for these types of bonds. I should say the name for the single bond is called a sigma bond. For the double bond, it's a sigma and a pi bond. And for the triple bond, it's a sigma and 2 pi bonds. All right. Scrolling down here. Let me see here. What was I going to teach next here? Yeah, we're here at this point. All right, let me pass out this sheet right here. We're at this sheet. I have this. This is the new sheet right here. So I'm going to pass that out. Right. We're doing sulfate, SO4 with a -2 charge. All right. And so I'm going to give you sulfate. This is where it gets a little bit harder. I purposely reviewed significantly right now so you could get what we just did. Now it's going to get a little bit harder. So pay attention with what we're about to get to. All right, because it's going to be everything. I'm trying to take you a step up a little bit more until we get to three-dimensional ones here. And so we're getting closer to three-dimensional. All right, so sulfate. Sulfate's got 6 valence electrons. 1, 2, 3, 4, 5, 6. All right. Oxygen's got 6 valence electrons. 1, 2, 3, 4, 5, 6. and there's 4 oxygens. All right. And then there's 2, it's a -2 charge, so I got 2 more extra valence electrons. All right, and so that's 6 plus 24 plus 2 equals 32 valence electrons. All right, and so we're going to start, the least electronegative element is in the middle, sulfur, boom. I'm going to surround it by oxygens. All right, I surrounded it by oxygens. How many bonds is that? 1, 2, 3, 4. That's a total of 8. So 24 minus 8. All right, that again, or not 24, 32 minus 8. Take that again. Whoops. That meant, because I was already thinking 24, it is 24. All right, and so, oh, that will work out perfectly. I can do 1, 2, 3, 4, 5, 6. I'm going to do it 4 times. 1, 2, 3, 4, 5, 6. 1, 2, 4, 5, 6. 1, 2, 3, 4, 5, 6. All right, that seems to make sense. Okay, well, that's easy. That's not hard. But here's the thing. There's a trick this here. Sulfur is part of period 3. And period 3 can have what we call an expanded octet. All right, an expanded octet. All right, that means it doesn't have to be an 8. It could be actually bigger than 8. All right, it can hold up more electrons. All right, and so we're going to see if this is the best one. And I have a video that I watched earlier about this, and I thought they explained it even better than me. And I wanted to start with the video and kind of explain it, let them explain it here. Okay. All right. And so let me do it this way. Boom. All right.
Hey besties! As you've probably heard, support for Windows 10 has ended. It made me realize my old laptop.
Hi, this is Dr. B. Let's do the SO4 2- Lewis structure. For the sulfate ion, on the periodic table, sulfur 6 valence electrons. Oxygen also has 6. We have 4 oxygens multiplied by 4, and these 2 valence electrons up here, we need to add those as well. That gives us a total of 32 valence electrons. We'll put the sulfur in the center, and then the 4 oxygens will go on the outside. Next, we'll draw bonds between the sulfur and the oxygens. So there we have 4 bonds, and we've used 8 valence electrons. Just go around the outer atoms and make sure they have octets. So we've used 8, 10, 12, and 32. Looking at the structure here, we see that each of the oxygens has 8 valence electrons, 2, 4, 6, 8, as does the sulfur here, 2, 4, 6, 8. But we're not quite done yet. Sulfur is in the 3rd period of the periodic table. That means it can hold more than 8 valence electrons. So we really do need to check our formal charges. So to calculate the formal charge on the sulfur, we see that sulfur on the periodic table, group 16 or 6,
All right, I wanted to tell you one thing about this.
has 6 valence electrons.
All right, so with formal charges, formal charge, we talked about formal charge on Monday. Okay, we talked about formal charge on Monday, and I started saying, okay, what is formal charge? Formal charge is this: it's the hypothetical charge on an atom on, and let me get this guy out of the way. The hypothetical charge on each atom in a covalent compound. And the reason why you want to know that, it helps you determine the Lewis dot structure correctly here, the one that's most likely to occur. All right, and so the one that has the least formal charge is going to be the one that's correct. How do you find formal charge? Formal charge is valence electrons minus the non-bonding electrons minus the number of covalent bonds, or you could say bonding electrons divided by 2, either one. And he's going to explain it a little bit better. And so I'm going to let him do it now.
Up here, all of the electrons, all of them are involved in bonds. So that's going to be 0. And the bonding electrons, 2, 4, 6, 8, we've used 8 of those, and we'll divide that by 2. 6 minus 0 minus 4 gives us a +2 formal charge for the sulfur. For the oxygen, it's also in group 6 or 16, so it has 6 valence electrons. Up here, non-bonding, we have 6, and then bonding, we have 2. And all these oxygens are the same, so we only need to do 1. So 6 minus 2 gives us a -1 formal charge for each oxygen. If we add up all the formal charges, the -1, -1, -1, -1, and +2, we do get a total charge of -2. That does make sense, but with formal charges, we want them to be as close to 0 as possible for the atoms. So let's see if we might be able to do another Lewis structure that has more zeros for the formal charges. When I see this +2 charge here on the sulfur, I know that I can move electrons from the outer valence electrons of the oxygen into the middle. So if I do that twice, if I move these two into the middle to form double bonds, get rid of them, I think that'll get rid of the +2 charge. So let's try that and then recalculate our formal charges. So I've moved electrons from the outside of these two green oxygens into the middle to form double bond. Let's see how that changes the formal charges. So for sulfur, 6 minus 0, there are no non-bonding. And now we have 2, 4, 6, 8, 10, 12 total bonding electrons. 6 minus 6, that gives us 0. So the formal charge on the sulfur is 0. If we look at the green oxygens, you can see we have 6 minus 4 of the non-bonding, and then 4 bonding. We divide by 2. 6 minus 4 minus 2 is 0. Finally, looking at the blue oxygens, we have 6 minus 6 non-bonding, and then 2 bonding. Divided by 2, 6 minus 1 is -1. So at this point, we see that we have mostly zeros, but if you look, you have a -1 and a -1 here. That works well with this. And since more of the formal charges are 0, this is a better structure for SO42-. Since it's an ion, there's one last thing we need to do. We need to put brackets around it to show that it's an ion and the charge of the ion. And we add our 2- right there. And that is the Lewis structure for SO42-. It was a bit of work, but we have the best structure here. Our formal charges are in good shape. We've used all the valence electrons. So that's it. This is Dr. B.
All right, so you can see how this person did it. So there's a little bit more to it than what we were talking about here now, especially when it comes to period 3, and especially when it comes to period 3 electrons here. So in fact, here's the ones I want to go back in our notes, all the way to this slide from earlier. I think that's on it. Here it is. Exceptions to the octet rule. Exceptions to the octet rule. All right. Elements in period 3 and typically beyond can have expanded octets. Expanded octets. And when they do that, they borrow the D level, because again, you're like, how does sulfur hold 12 electrons? Okay, how does sulfur hold those 12 electrons? It's got those p orbitals. Well, it borrows the d orbitals that are also that third energy level to help with it. But again, it doesn't get the electrons too much either. All right, because it's with these electronegative oxygens. All right, and so that's what we're showing right here. So again, you're supposed to write the stuff that's bold and underlined, because that means that I have not written that on your paper. I did see your hand. I'm not ignoring it. I was just trying to show that here. All right. What were you saying, Lily?
So it's the reason that sulfur has a -2 charge because it has 2
Oxygen ions. All right, yeah, it's going to have, when we go back to what he was drawing at the end, All right, what he was drawing at the end right over here. It's got an oxygen ion here, an oxygen ion here that has a little bit of a negative charge, and it's going to have the non-oxygen ions right here. But we're going to also see that this is actually we're going to see that this is also a resonance structure. That means the electrons kind of rotate between all of these oxygens. We're going to be talking about that tomorrow. So you're ahead of the game, but we're going to see that coming up. So going back over here, we've done that. Oh yes, I wanted to show you something on the notes. All right. Formal charge, here it is. All right. Formal charge. Again, at the top, it's a hypothetical charge on an atom in a covalent compound. That's what it is. That stuff is underlined and bolded. That's what you need to write down. I do check these notes later. All right, this is on the new notes. This is the new notes that I just gave you. All right, so formal charge. The formula for formal charge, the one I like personally, the one I like best is this one right here. This one, I want to go back. This one right here. This is the one that I like best because valence electrons minus non-bonding electrons minus covalent bonds, number of covalent bonds. All right. And so that's how I like to do it. Now, he did them with, he did the top one, valence electrons minus non-bonding electrons minus bonding electrons divided by 2. And again, it's the hypothetical charge on each atom. It is time for us now to do our next problem. We're going to do it together, though. So we're going to do it together. Going to phosphate, PO4, -3. So PO4, -3. All right. So we're going to do this one together here. Oop. All right. So PO4, -3. All right. First thing I do is I do what? Yeah, I do all the before structures. 1, 2, 3, 4, 5. All right, oxygen 1, 2, 3, 4, 5, 6 times 4. And then I have +3 valence electrons. All right, so I do 6 times 4, that's 24. That's 5. And this is 3, and that gives me 32 valence electrons. All right. So first thing that we're going to put that phosphorus atom in the middle. Okay. Then we're going to surround it by oxygen, single bonds. We always do start off with single bonds. This is trial and error. That's what this is called. All right. Single bonds. So 32 minus 2, 4, 6, 8. I get 24. All right. I can put these 24. I need, how many more do I need for each oxygen? 6. So 6. If I do that, 6 is 6 for every oxygen, then I'm done. Or so am I. All right, so I got all my dots in a row. All right. And so now we need to calculate the formal charge. Formal charge is equal to what? Help us out with the formal charge. All right, let me get all my volunteers out. Let me get here it is. All right. All right. Esmeralda, what is the formula for formal charge? Almost valence electrons minus non-bonding electrons minus bonding electrons divided by 2. So it's all of those, okay? All right, so we've got to do this for nitrogen. So nitrogen's formal charge. This is what we're doing first. Nitrogen's formal charge. That's like a colon. All right, so nitrogen has, Ella Grace has how many valence electrons? Huh? Phosphorus. All right, Ella Grace, it's phosphorus has how many? 5. All right, thank you. All right, it's got 5. Ella Grace, how many non-bonding electrons does phosphorus have? All right, non-bonding means there's electrons by itself around phosphorus. We have 0. All right. How many bonding electrons do we have over here? How many are there are 2 electrons in every bond. So how many electrons do I have total? 8. So 8 divided by 2, and again, this is the way Esmeralda told us the formula. So I get 5 minus 0 minus 4, which equals to 1, positive 1. Right? The oxygens, so this is positive 1 right here. Okay? The oxygens have how many valence electrons? Gabby? 6. All right, how many non-bonding do they have? Yes, that's right. And how many bonding do they have? So 2 divided by 2, which is going to be 1. And so that's going to equal to -1. Every one of these are -1. All right, so this has got a lot of charges on it, okay? This has got a lot of charges on it. And so that makes me think, probably not the structure, But does it equal -3? -4 plus 1? Yeah, that's -3. This could be it. This could be a possible Lewis structure. So we're going to do it one more time, but this time we're going to change one of those bonds to a double bond. And this is the phosphate that's in ATP. Okay, same thing that it's adenosine triphosphate. This is the phosphate that's in ATP. There's 3 of them in ATP. This is the phosphate that's in DNA, making up nucleotides in DNA. So this is the same phosphate type of thing. So this is again the structure of phosphate. So we had 32 valence electrons minus how many? So how many do we have in bonds, Rudy? Ten. So I have 22 left. All right. The oxygens are in period 2, so they have to have an octet. All right, and so that means how many more will this one need, Lewis? 4 more. So out of those 22, I took away 4. Now there are 18. All right, every one of these oxygen needs how many more? 6. So if I just give them all 6, I think that'll be good. Let's see if that works. All right, so this is our second model. Let's see if this is a better one. All right, phosphorus has how many valence electrons? Irene. 5. How many non-bonding electrons does phosphorus have? 0. How many bonding electrons does it have? All right, it's got 2 here, 4, 6. There's 2 in every one. So there's how many if there's 2 in each bond? It's 10. So all right, minus 10 divided by 2. That's what they were just telling us that formula. So that will equal 0. So the phosphorus has a 0 charge. Okay. The oxygen, for the top oxygen, one with the double bond. All right, the top oxygen with the double bond has How many valence electrons? Allie. And how many non-bonding does it have on it? Not this one right here.
Attention teachers and students, at the sound of the bell, I need all state swimmers to report to Mr. Craigsford. At the sound of the bell, I need all state swimmers to report to Mr. Craigsford. Thank you.
And how many ones and bonds? 4. All right, and that will equal to 0 again. So this one's got a 0 charge too. And we've already calculated the ones with this. These are -1. That is a better structure because it has less charges. You said, why does charges matter like that? If you have more areas that are charged, yeah, it's more unstable. It's more reactive. Okay, it's more reactive. And so therefore you want the least amount of charges. Now, somebody might go say, well, what if we did 5? Why don't we do 6? All right. Well, the problem is then you're going to have phosphorus with a negative charge. Phosphorus is going to have a negative charge, and phosphorus has a lower electronegativity than oxygen. So who should get the electrons more often? Oxygen or phosphorus? Oxygen. So oxygen, you should not have, phosphorus should not have have a negative charge, and some of the oxygens have a 0 charge. That's not going to work. Okay. And so we got to have that like this. This is our best structure right here. All right. Now your homework. All right. Your homework. Your homework is to do, I'm going to give you this sheet. You're going to do 1, 2, 3, and 4, and 7 on back. All right. 1, 2, 3, 4, and 7 on back. All right. And that's going to be your practice on this. If you don't, I will check homework tomorrow.